Unit 1.11, defining continuity at a point. The formal definition of continuity. For f of x to be continuous at x equals c, the following three conditions must be met. 1. F of c must exist. 2. The limit as x approaches c of f of x must equal the limit of f of x as x approaches c from the right must also equal the limit of f of x as x approaches c from the left. 3. The limit as x approaches c of f of x must equal f of c. Number 1. State whether the function f of x is continuous at the given x values. Justify your answer. So the first x value is x equals -1. So since x equals -1, sorry about that. First, we just want to see if f of -1 exists. So, or not, you know what I'm trying to say. So we'll say f of -1 is, use this equation right here. So it's -1 plus 2 equals 1. That exists. So now we're going to test it from both sides. X approaches -1 from the left equals, so we're approaching from the left, we'll use this one since x is less than -1 and it's approaching from the left. Plug it into this equation, and that is -1 squared minus 2 of negative multiplied by -1 plus 1 equals 4. And then we want to check it from the right. F of x, so x approaches -1 from the right. Since it approaches from the right, we'll use this equation since x is greater than -1. And -1 plus 2 equals 1. Since they don't match up, no, it is not continuous. X equals 2. Again, I want to plug 2 into f of x, so we'll say, we'll use, well, it doesn't really matter, but we use that one, and then, so it equals 4. Start from the left, so the limit of f of x as x approaches 2 from the left. So it is approaching it from the left, it has to be less than 2. And so we'll use this equation since x is less than 2. Plug in 2, so 2 plus 2 equals 4. And the limit of x plus 2, it approaches 2 from the right. Since it's greater than 2, we'll use this equation. 2 squared equals 4. Since it matches up, we'll say since the limit of f of x as x approaches 2 equals 4, it equals f of 2. So yes, it is continuous at x equals 2 because they all match up. Alright. Identify the type of discontinuities, if any, and where they occur. So we'll do, since it's dealing with 4 right here, we'll check 4 from the left and 4 from the right. So the limit of f of x as x approaches 4 from the left, since it's from the left, we have to use this equation. 3, 4 plus 1, 12 plus 1, 13. The limit of f of x as x approaches 4 from the right We use this equation, 4 over 2 minus 1, that's 2 minus 1, this equals 1. Since these two are very far apart, we know that this is a jump discontinuity. For this one, we're going to be wanting to check the limit of 1. So check it from both sides. The limit of g of x as x approaches 1 from the left, less than, so we use this one, -1 squared plus 2 multiplied by -1 minus 1 equals -2. And then the limit of g of x as x approaches -1 from the right, we'll use this equation, so -1 minus 1, which is -2. Since these two are equal, but between these two, when it is equal 1 and, well, from these, when it's equal -1 is 5, but when it's less than, when it's approaching, it's -2. So since it's such a large difference, we know that is a removable discontinuity. Let h be the function defined by h of x. What value of k would make h continuous? Okay. So we'll start by checking the limit from both sides. So the limit of f of x as x approaches -2 from the left, use this equation, equals 2 minus -2 squared, so then this equals -2. And then the limit of f of x as x approaches -2 from the right, we use this equation, and then it's 4 -2 plus k equal, and this just equals -8 plus k. Now to find what value of k would make h continuous, we need to find, well, what value of k it is. So we make these two equal to each other. So -2 equals, -8 plus k. We do plus 8 on both sides. K equals 6. So the value of k equals 6 makes h continuous.